We spend our entire lives moving through invisible oceans, from the aerodynamic forces gripping the wings of a jet in flight to the pulse of blood rushing through our own veins. We are surrounded by powerful currents that our eyes simply cannot see. Because we are blind to these forces, our first instinct is to try and capture them on paper. We write elegant mathematical models to simulate what we call ideal flow, a simplified, predictable set of rules where liquids and gases behave with perfect manners. If you look at this mathematical model of fluid hitting a simple cylinder, the lines of flow part, glide smoothly around the obstacle, and rejoin seamlessly on the other side. It is a clean, reassuring picture. But those perfectly symmetrical lines are a complete fiction. Nature rarely behaves that politely. Real fluids have friction. They have viscosity, causing adjacent layers to stick and drag against each other, and they have inertia, meaning they resist sudden changes in direction. Those physical properties instantly break the perfect symmetry our equations expect. Look at what happens in an actual physical simulation of that exact same cylinder. The fluid doesn't glide, it tears. The current sheds these alternating, swirling pockets of low pressure in its wake, creating what physicists call a von Karman vortex street. The standard idealized equations completely missed this chaotic structure. To build a suspension bridge that won't twist in a storm, or a pacemaker that won't trigger blood clots, engineers cannot rely strictly on the math. They have to run physical experiments and force the invisible world to reveal its messy reality. The oldest and most intuitive way to see a current is simply to throw something visible into it. For over a century, scientists have pumped smoke into wind tunnels and dropped colored dye into water tanks. Dye can trick you. A single particle leaves a historical trail called a path line. A continuous dye stream creates a streak line, instantly warped by any spinning vortex. Assuming this warped streak represents the actual fluid path will make an engineer's calculations entirely wrong. Modern aerospace design requires hard numerical datasets. To optimize a wing or a turbine, engineers need to map the exact velocity and local acceleration of every particle in the field. This laser map shows particle image velocimetry. By seeding the air with microscopic tracers and firing a thin sheet of laser light, we illuminate a precise slice of airflow. High-speed cameras capture the displacement of these glowing dots over time, calculating millions of exact velocity vectors. There is a catch. If your tracer particles are too heavy, their own momentum will fling them right out of the tightest curves. To get accurate data, our tools must perfectly mimic the fluid they are trying to measure. But what if you are testing the aerodynamics of a jet flying at supersonic speeds? You can't safely inject tiny particles into air moving faster than the speed of sound. Instead, researchers exploit a quirk of physics known as the Gladstone-Dale relation. When a fluid compresses or expands, its density changes. And when density changes, it literally acts like a lens, bending the light passing through it. We can capture this bent light using Schlieren photography. By placing a precisely aligned knife blade at a camera's focal point, we filter out straight, undisturbed light. Only rays bent by sudden pressure changes slip past the blade to hit the lens. Take a look at this high-speed test. Without the optical filter, you would see nothing but empty background space around the jet. But because that knife edge blocks the ambient light, the violent, invisible walls of compressed air, the shock waves, appear as bright, sharply defined lines. If we swap that sharp blade out for a multicolored filter, we get this, a map that assigns vibrant, distinct colors to quantify the exact severity of the density gradients inside a turbulent flame. Optical techniques let us use the fluid's own physics as a magnifying glass. We can observe extreme thermal and aerodynamic forces entirely undisturbed. In fluid physics, behavior is often dictated by ratios rather than physical size. By matching these ratios, like the Reynolds number, which balances inertia against viscosity, the same governing equations can be applied to flows at vastly different scales. This universality allows us to scale our tools down. Here, a researcher uses micro-PIV to observe flows that are invisible to the naked eye, not because of transparency, but because of their microscopic size. Using intravital microscopy, biologists can now peer directly into live blood vessels to watch white blood cells navigate the rushing current. In this footage, you can see the mechanical reality of the immune system. To stop at an infection site, a cell must grab the vascular wall and apply the brakes against the tearing force of the blood flow. Mathematical formulas give us a clean, idealized starting point, but they require assumptions that the physical world rarely respects. Whether we are trying to design a safer aircraft or understand how our bodies fight off disease, forcing the invisible world to reveal its beautiful, chaotic truth is the only way we can learn to navigate it.